Hello everyone. In today's session, we will be doing something new. Like in real numbers, we have seen various mathematical operations, square roots, cube roots, etc. Now, in previous session, we have done up to say square roots. So in this session, we will be starting with cube roots of unity, which is a very standard part of complex numbers. And also, we will be spending some time on special cases of multiplication. So let me start with first cube roots of unity. Unity means 1. Cube root, you already know. So if I say z is a cube root of unity, then obviously z would be written as 1 raised to 1 by 3, which by taking cube on both sides will be z cube equal to 1. I mean, this is very standard thing which you already know. Now we have to solve a cubic equation. Generally, methods of solving a cubic equation are tedious, but some standard techniques we try to apply. That you substitute some values, and if both sides become equal, then one of the roots can be obtained. So z equal to 1 by observation is surely a root. This is one way of understanding at least one root. Another way could be that you write this as z cube minus 1 equal to 0 and factorize z cube minus 1, which leads to z minus 1. Another factor is z square plus z plus 1. Now that z minus 1 equal to 0 would lead to that root, what I said just now, z equal to 1. And other two roots are expected now from z square plus z plus 1 equal to 0. Now when you solve z square plus z plus 1 equal to 0, it is a quadratic equation and discriminant is negative. So now since discriminant is negative, we are expecting some non-real roots here. So what are those other two non-real roots? One is minus 1 plus I root 3 upon 2. And other is minus 1 minus I root 3 upon 2. Now here I have straight away written by not showing actual calculation. Now that much calculation you can do by solving it as minus b plus minus under root b square minus 4ac upon 2a, which leads to these two non-real roots. Now these two non-real roots are called actually non-real cube roots of unity. And if you just go back in your memory, you will realize that in your previous classes, you were not able to find other two cube roots. I don't know how many of you had paid attention to this, that whenever you are solving for cube root, there have to be 3 cube roots. Whenever you are solving for square roots, there have to be 2 square roots and so on. Now, 3 cube roots were expected, but you were all the time trying only z equal to 1 kind of, which is a real root. Now, other two were actually non-real ones, and that's why perhaps you were not in position to get them. Now, one of them is called omega, which is minus 1 plus I root 3 upon 2, and the other one I have deliberately written omega square only. And that omega square is minus 1 minus I root 3 upon 2. Now, you may think that I could have given some other name also instead of omega square. The thing is, when you actually square omega, you will get that remaining root, which is minus 1 minus I root 3 upon 2. So why to give a special name? So let me write it as omega and omega square. And this is a very, very standard notation. So what we have done is one real root, which is z equal to 1, and two non-real roots, omega and omega square. So in all now we have 3 roots, 1, omega and omega square. Now these omega and omega square, which are actually cube roots of unity, they have some special properties. So let's go towards the properties and revise once more that these two non-real roots are conjugates of each other and one is square of other. I am generally saying one is square of other. Actually, if you square omega square, you will get omega raised to 4. And since omega satisfies z cube equal to 1, so omega cube is 1. So omega raised to 4 would be written as simply omega. So if you square omega square, you get back omega. Or if you square omega, then you get omega square. So one is square of other. Okay. So let's proceed towards properties. Now properties of cube roots. First thing, very standard, which you are expecting, omega cube equal to 1. No need of any explanation, I guess. Now second one is 1 plus omega square equal to 0. Now ways are there to understand this. Omega is already known to you. You substitute omega and omega square and then add 1 to it and simplify, you will get answer 0. This is but longer way. Now other explanation could be that omega and omega square satisfy the second factor, which was z square plus z plus 1. Right? So z square plus z plus 1 becomes 0 when you substitute z equal to omega or z equal to omega square. And hence I can say 1 plus omega square is 0. This is another explanation. And there is one more nice explanation. You can think what you have done in your quadratic equation part. There also we had tried to solve some higher degree equations. So cubic ones also we had tried there. So what I observe is that since equation is z cube minus 1 equal to 0 and there is no term of z square, so coefficient of z square would have come for sum of the roots. And now since coefficient of z square is 0, so sum of the roots is 0. And what are three roots? 1, omega and omega square. Sum of them is 0 means 1 plus omega square equal to 0. Now these two are some standard explanation. Why do we have 1 plus omega square equal to 0? I think this is good enough. Now I move to next, and next one is all three cube roots of unity. They would lie on mod z equal to 1. Why do I say so? Because if you check taking modulus of each of 1, you will realize obviously 1 has modulus 1. Modulus of omega and modulus of omega square, they also happen to be 1. And hence those three cube roots lie on unit circle mod z equal to 1. Which you can actually check in the figure. And how would it look? It would look something like this. That I have shown position P for z equal to 1. I have shown position Q for z equal to omega. And I have shown position R for z equal to omega square. And actually if I join them, I would understand that by joining OQ and OR, why do I join OQ? To get argument of omega. And why do I join O to R? To get argument of omega square. Yes. Now, if I join P, Q and R, that figure actually looks a very standard figure. Okay. So what we understand is that if we place those three cube roots of unity on unit circle, then actually triangle PQR happens to be nothing but an equilateral triangle. Why is it so? Now next property will make it more clearer. Actually, argument of omega is 2 pi by 3, and hence since OP and OQ, they are equal, you can understand what would be angle QPO or angle PQO. They are equal, and hence you know that what is angle finally PQR, and that is nothing but 60 degree. So this is another explanation to understand that why we have equilateral triangle. What is argument of omega and omega square? 2 pi by 3 and 4 pi by 3. This I am writing from the standard expressions for omega and omega square by putting them in polar form. I have already spent some time on getting how do we find argument, right? So these 2 pi by 3 and 4 pi by 3 directly I have written by converting omega and omega square's expression to polar form. The next one is a plus b omega plus c omega square, and a plus b omega square plus c omega. If you multiply, it gets into an expression which is free of omega, which is a square plus b square plus c square minus ab minus bc minus ca. And this expression you have already seen somewhere. If you recall your algebra of lower classes, I mean 7th or 8th standard algebra, you will understand this expression we had seen in expansion of a cube plus b cube plus c cube minus 3abc. Okay. Now we have expression for a square plus b square plus c square minus ab minus bc minus ca, which is a very standard expression which we have seen in the expansion of a cube plus b cube plus c cube minus 3abc. If that is the case, then I can always factorize perhaps a cube plus b cube plus c cube minus 3abc in terms of omega and omega square. Now three factors are expected because it is a cubic polynomial, and there is a standard result which says a plus b alpha plus c alpha square is a factor of a cube plus b cube plus c cube minus 3abc. If that is the thing, then I can replace once alpha by 1, second time by omega, and third time by omega square. So all three factors are known to me. And hence I can always write a cube plus b cube plus c cube minus 3abc equal to, one step I have not written, I have directly written the result. Factors would have been a plus b plus c, a plus b omega plus c omega square, and a plus b omega square plus c omega. These three factors are expected, right? Why? Because that a square plus b square plus c square minus ab minus bc minus ca have been replaced by the product of those two factors which have omega and omega square in them. So these are standard properties of cube roots of unity. Now let us move towards some special cases of multiplication. Why am I taking it? Because once I take at this place, your problem solving sessions would be more easier. Instead of repeating them again and again, let me have here itself. Now my first special case is that if I multiply a complex number z by I, then what happens? Now, when we were doing the multiplication part on Argand's diagram, I have emphasized on this that you try to write a complex number in polar form. So I write z as r into cos theta plus I sin theta. See, I have already avoided to write it in the form of Cartesian one. I mean x plus iy. I'm avoiding. And I want to now multiply by I. So obviously, even I write iota. I write I as in polar form. And if I write it in polar form, I would understand that its modulus is 1. So that r into cos theta plus I sin theta, what we write, that r is 1. And argument is pi by 2. Now, hence, I becomes cos pi by 2 plus I sin pi by 2. When I multiply z to I, what will happen? Now, since modulus of I is 1, so modulus of z and modulus of the product zi will be same. So, r comes as the modulus. And now, argument will become pi by 2 plus theta. Now, let us understand this on Argand's diagram. So, draw your real axis, imaginary axis, mark that point P, which represents z, and also mark correspondingly that position Q. Now, how do we do it? That I have already shown theta, and I have already seen in that multiplication that I need to rotate now OP by angle pi by 2, because new position is for pi by 2 plus theta. And hence, position Q would be marked after rotation of OP, right, in which direction? Anti-clockwise direction, and mark length OP same as length OQ. So that position of Q will represent Zi. So multiplication by I, how does it happen on the Argand plane? It is just pure rotation. So geometrical interpretation of multiplication of I is that we need to rotate OP by 90 degree in anti-clockwise direction. And also we observe that there is no length change, there is no modulus change. So it is a case of pure rotation and no shear involved here. Now let me take one more case, that you multiply by omega. If I multiply a complex number z by omega exactly on the similar lines as the previous one, we proceed. That z equal to r times cos theta plus I sin theta, right? Then I try to express omega in the polar form, and polar form would be cos 2 pi by 3 plus I sin 2 pi by 3. Modulus of omega is 1. And when we write z omega or omega z, the modulus will be r, same as z, because modulus omega is 1. And then now new argument of that product form would be theta plus 2 pi by 3. If that is the thing, then again I will have to mark on real axis, imaginary axis, that point P, and then some rotation is expected. Now what kind of rotation? Rotation by 2 pi by 3 in anti-clockwise direction to get the direction of actually z omega. And since length part is same, so length OP and length OQ would be same. So mark Q accordingly, and that position of Q will be nothing but representing the z omega point. So basically, geometrical interpretation here is that you will have to rotate by 2 pi by 3 or 120 degree in anti-clockwise direction. And also, what we have observed here also, it is a case of pure rotation and no shear. So multiplication by I and multiplication by omega, both are the cases of pure rotation. Now let me move to the next one. And the next one is that what do we mean by argument of z1 upon z2? How do we interpret it? When I say interpret, I'm expecting this to happen on the Argand plane only. So obviously, I take, suppose, argument of z1 upon z2 as theta. I have to understand what that angle theta means. I hope you understand what I'm saying. Interpretation means we should be able to understand that where do we show that theta on the Argand plane. Okay, so mark your real axis, imaginary axis, as we do, and I mark, suppose, position Q, which represents Z2, and I mark position P, which represents Z1. Then argument of Z1 upon Z2 is, if I'm calling it theta, then theta would be the angle between OP and OQ. Now that is the geometrical interpretation. And mind you, please, direction is important. That theta I have shown in anti-clockwise direction. That means OQ needs to be rotated in the direction of OP, right? Now, how do we remember it? I mean, when you solve problems, you should be able to understand that what we are going to do. Quantity which appears in the denominator, that is Z2 here. So, point representing Z2 is Q. So, OQ needs to be rotated to get in the direction of the number which appears in the numerator. So, P represents Z1 and Z1 appears in the numerator. So, we have to go to direction of OP. So OQ needs to be rotated in direction of OP in anti-clockwise direction by theta. That is the interpretation, right? So this is how we have understood special cases of multiplication and interpretation of argument of Z1 upon Z2. When we meet next time, again I will come with something new. Hope you have liked this video. To subscribe, please click here, and if you want to place an order for the book, please click on this side. Thank you.